Welcome again, ladies and gents, to another flipped lesson. Today what we're going to focus on is understanding what this word called enthalpy means, which means we're putting heat into the mole map, my friends. Get ready for some exciting stuff. Let's get started. So when we talk about chemistry in terms of a reaction either needing energy or giving energy off, we think of this as something called enthalpy in the chemistry world. And so what this enthalpy means is it's delta H, and it's going to be the heat that's either produced by the reaction or the heat that's needed in order for a reaction to go. So what you'll see in a thermochemical equation is at the end, you'll see this little delta H guy here. And what that tells you is this is the energy transfer for that chemical reaction. So what we're looking at right now is we're looking at the synthesis of calcium hydroxide. And in that process, we can see that we have a delta H of negative 65.2 kilojoules. So if we think about what we know about heat, would this reaction be endothermic or exothermic, and why? We've got a negative symbol here, which means the reaction would be exothermic. So if we were to think of this in terms of a reaction diagram, where we know we've got our potential energy going up the y-axis, and we've got our reaction course going on the x-axis, what would happen in order for us to have a negative enthalpy change is our calcium hydroxide and our water, calcium oxide and our water are going to have a higher potential energy than our calcium hydroxide that we're making. And so that means this drop in enthalpy, this drop in energy, is going to be a negative 65.2 kilojoules. So there's more energy in the bonds of our reactants than in the bonds of our products. So this little negative sign out front tells us that it's going to be exothermic and energy is going to be given off by this chemical reaction. So if we saw a delta H that was positive, that would mean that the reaction is then endothermic. So if we think of our old mole map here, so we have, moles and volume and grams and particles and all that kind of stuff, how exactly does heat tie into this? Where heat comes in is through the idea of moles. And so what you can do is you can think of this as kind of like a modified mole ratio. So when you're doing a thermochemical equation, you're not going to go through what we would typically call the mole ratio. You'll go through this little modified area where you're going to link the delta H into heat using the coefficients of the chemical reaction. So if we look at an actual practice problem, we have a reaction here. It says I've got 2.24 moles of NaHCO3. How many kilojoules are needed to decompose this? So the first thing we want to do is we want to think about what is the chemical reaction. So since it's decomposition, I only have one reactant and I've got multiple products here, and we can see my enthalpy of the reaction is 129 kilojoules. Since this is positive, that means this is going to be an endothermic reaction. So we're going to need 129 kilojoules to actually decompose this sodium bicarbonate. Now, how we link these two things together is it's just like a recipe. So since our coefficient is 2 in front of our NaHCO3, that means for every 2 moles of NaHCO3 that I put in, I am requiring 129 kilojoules of energy in order for the decomposition to actually take place. So we can set it up just like a dimensional analysis problem. So this is going to be our link between moles and heat. So we want to know how many kilojoules are needed to decompose 2.24 moles of sodium bicarbonate. So from my reaction, I know that every time I put 2 of these in, I require 129 kilojoules. So my units cancel. My 2 moles of NaHCO3 are going to go on the bottom, and my 129 kilojoules of energy that I'm requiring is going to go on top. My moles cancel, I'm now in kilojoules, so I'm going to go ahead and multiply 2.24 times 129 and divide that by 2. Since this has 3 sig figs to start, my answer can only have 3 sig figs, so when you punch that in your calculator, you get an answer of 144 kilojoules. So since I'm putting a little bit more than 2 moles in, I'm going to require a little bit more energy to decompose that. Now, if we think about the mole map, the only thing that would be different would be if I asked you to start someplace else. So for that problem, I just went between moles and heat, but we can in theory start anywhere. I could give you a mass, and you can go from mass to moles to heat. I can give you particles, and you can go from particles to moles to heat, or I could give you like a volume of oxygen that's being combusted, either at or not at STP, and we can go from moles to heat. Now I'm going to give you a hint. We're typically going to either start here or here for our heat problems. So that's it. It's just understanding that the link between your coefficient will tie you into your heat, and you can solve any thermochemistry problem. So what I'd like you guys to do right now is this problem right here. This is the one I'd like you to provide your answer to on the Google form. And remember, if you have any questions, you can always come in early and ask or shoot me an email. Tomorrow, what we're going to learn is how we actually get these delta H numbers. So today, we just wanted to know how to use them. Tomorrow, we're going to learn how we actually get them. Have a great night, guys.